All right, so we're going to continue on with chapter 10. And this is looking at, in 10.5, and looking at a little bit more on the counting stuff. So here we're going to look at something called permutations and combinations. So to get the idea of it, those are two big words. And the words that are kind of used in English, normally combination probably more so than permutation. We don't say permutation that much, but combination we say a lot for a lot of things. And in this context, those words have specific meanings. So a lot of things in regular speak will say combination for everything. But here we're going to draw a distinction between some things are combinations, but other things are permutations, which is slightly different from combinations. So let's go through this so we can see what those differences are, and try not to get too bogged down in the words, but think about like what it's actually saying. So let's compare two situations. We're going to buy a 3-scoop ice cream sundae. We can either get the sundae in a bowl where we have enough space to have the 3 scoops next to each other, or we can get it on a cone where the scoops are stacked on top of each other. If I get a bowl, so let's say this is my bowl, looking at it top down, and let's do chocolate, right? So I can have chocolate, I can have vanilla. Let's put some vanilla flecks in there, and then strawberry. That also looks like a really weird face. Okay. My drawing skills aside, if I do another bowl, the only thing I can change here is the order I put these things in. Right, so I could put the strawberry on this side, I could keep the vanilla here, and the chocolate over here. But it's not really changing the bowl of ice cream. I can still, because if I just rotate this, it's going to look the same as the other bowl. So these really aren't different bowls. There's really just one bowl of ice cream I can make. This is basically the same thing. Let's keep that off to the side. Now let's think of cones. With the cone, I can put chocolate, and then strawberry, and then vanilla. I can go chocolate, vanilla, and then strawberry. I can go vanilla, chocolate, and then strawberry, and so on. I can change the order of these scoops, and now I'm making different cones because in this case, whatever's on top, that's the one you eat first. Probably the one on the bottom, that's the one that's going to sink down to the bottom of the cone. By the time you get there, the other ice cream would have melted down into it, so the flavors mix up a little bit. So it's not as separate from like in the bowl where like it doesn't really matter which order you put the scoops in. In the cones, the order matters more because the order of those scoops changes how you taste this. So the bowl, this is a situation where order doesn't matter. Right? The order I put the scoops in doesn't change my overall bowl. For the cone, the order I put the scoops in changes my cone. And so here the order matters, whereas in a bowl the order doesn't matter. That is the fundamental difference between a permutation and a combination. When the order matters, that is called a permutation. When the order doesn't matter, that's called a combination. So let's fill those in. When the order matters, we use a permutation. And I'm going to write the formula down for it. Now the formula is going to look a little scary. There's going to be a lot of new symbols in it, but we'll go through it slowly. So the formula for this looks like NPR, not National Public Radio. Just N, capital P, subscript R. So that's the notation for it. Here the N is the total things you can pick from. And R is how many things you're picking. So, for example, in my cone, I had 3 different flavors, so I had totally 3 things I could pick from. And then I was also picking 3 flavors from it, so 3P3. P is permutation. So now the formula to calculate that looks like this. N exclamation point divided by N minus R exclamation point. So it's not just those letters being really excited, although you could think of it that way, maybe. They're so excited that they make this thing called a factorial. And a factorial is kind of like a shorthand way of writing something. In this case, a factorial is, for example, if I had 3 factorial. Right, so I have 3 exclamation point, really excited 3. What that means is it's so excited, it's going to go down to all the numbers less than it and multiply with them. So it's going to go 3 times 1 number less, 2 times 1 number less, 1, and then we stop at 1. So anytime we're doing these factorials, you just keep going down the numbers until you get to 1, and then stop. So 3 factorial is the same as 3 times 2 times 1, which is 6. Similarly, like if I had 6 factorial, so 6 is really excited, it runs down the line, goes 6 times 5 times 4 times 3 times 2 times 1, and I stop at 1. And I have to multiply all of that out. That one you can type on your calculator. Your calculators do have factorial buttons on them. So if you find that button, you can just use that factorial button. In some of your calculators, it's buried under the probability, like you have like a PRB button probably on your calculator. If you click that, that probably is the factorial button might be inside that, if it's like not on the actual button list already. And then if you have that probability button on your calculator, you also have buttons for permutations and combinations in there. It'll be written as NPR and NCR. You can use those to check your calculations as well, to do it on a calculator. So like in this case, 6 factorial of 720. These are really big numbers with factorials because they're multiplying a lot. So we write the factorial to just like write it smaller. So if I was using this formula, I take my n value, the 3 here, and I factorial it. And I go 3 minus 3 factorial. So 3 factorial on the top is 3 times 2 times 1. And then 3 minus 3, that's 0. The one weird thing with factorials is we just say that anytime you get 0 factorial, that equals 1. We don't do anything with like the 0 times anything because then it's always 0. But as like a definition, when people came up with the definition of what a factorial did, you said for all the other numbers, you just go down until you get to 1. For 0, we're going to just make a special rule for it. 0 factorial equals 1. It's because like the purpose of factorials was to do stuff like this, and then when you're doing problems like this, you don't want it to be 0, you want it to be 1. So in this case, the 0 factorial is just going to be 1. So I get 3 times 2 times 1, 6 possibilities. So this is saying that there are 6 different cones I could have made, which makes sense. I had 2 with chocolate on the bottom. I can have 2 more with vanilla on the bottom. I can have 2 more with strawberry on the bottom. That would make my 6 possibilities. Now let's do the next one when order doesn't matter. This is called a combination. And we write this as NCR, where N and R mean the same thing. N is the total things you can pick from. R is how many things you're actually picking. In this formula, it looks similar to the permutation formula. It starts off the same way. Because combinations are really just looking at these permutations and then saying that like these 2 things in a combination are the same because they have the same, like all of these are the same because they have chocolate, vanilla, and strawberry. The order we put them in doesn't really matter. In a combination, all of these things would be the same thing. And so it starts off with looking at all the permutations, and then it gets rid of everything that's a repeat of something else. So to get rid of all those repeats, we multiply by r factorial on the bottom. The reason this works isn't too important. The main thing I want you to get out of this is knowing the difference between when something is a permutation and when it's a combination. That's your main learning goal, is to differentiate. Like, if I tell you a scenario, you should tell me, does that scenario represent a combination or does it represent a permutation, and then just calculate it. The reasoning behind the formula isn't too important right now. If we were doing this in person, we would go more in depth into like how that formula comes about. So with this formula, if I used it on my combination, now with the bowls, there's only one bowl I can make because I have 3 flavors and I'm picking 3 of them. So no matter how I pick them, I'm going to get the same bowl every single time. So I should get this equal to 1. So let's see. I go 3 factorial, n factorial on the top, and then 3 minus 3 factorial for the n minus r, and then r factorial, which is another times 3 factorial. So go 3 times 2 times 1 divided by 0 factorial, which is 1, times 3 times 2 times 1. The 3 times 2 times 1 cancels. I just get 1 at the end, which is our 1 bowl, which makes sense from our drawings of this. So again, main thing to remember is what is the difference between a combination and a permutation. When the order matters, it's a permutation. When the order doesn't matter, it's a combination. The main like dad joke kind of thing with this is a combination lock. So in a combination lock, the order actually matters, so they should be called permutation locks, not combination locks. Haha. Yeah. So let's look at some examples with this. So we have 8 people, and we want to know how many ways we can award first, second, and third place to them. So the first step on any of these problems is to know if it's a permutation or if it's a combination. So first step, does the order matter? So let's think about this. If we have 8 people, let's name them A, B, C, D, E, F, G, H. And let's say A comes first, and then I pick B to come second, and I pick C to come third. Is that different from if I pick the same 3 people, A, B, and C, but now I pick C first, then I pick A, and then I pick B? In this case, it is different, because based on how I pick them, it changes which place they get, which prize they get. And so here the order matters, because depending on how I picked the people, it changed what prize they got. So here the order matters. And because the order matters, it's a permutation. So then we calculate it. So I have 8 people, 8 total people to pick from. I'm doing a permutation, and I have to pick 3 people from those 8. So I go n factorial, so 8 factorial, divided by 8 minus 3 factorial. So that's 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, divided by 8 minus 3 is 5, so 5 times 4 times 3 times 2 times 1. Those can cancel, so I just get 8 times 7 times 6, which is 336. So there are 336 different ways we can award first, second, and third place. Now let's do a different scenario. Still 8 people, they're volunteering for a job, but I only need 3 people from those 8. In this case, again, we ask ourselves, does the order matter? So here I have 3 people doing the same job that they're volunteering for, but there are 8 people who want to do it. Would I pick, if I'm picking the same people, right? So I do A, B, C, D, E, F, G, H. Let's say I pick A, C, and D. Is that different from me picking the same 3 people, but in a different order? So I'll do C, D, and then A. It doesn't matter which order I pick them in. It still gives them the same people are still picked. And that's all that matters. So here the order doesn't matter. So this is a combination. And so when we calculate this, we go 8C3. And that's 8 factorial divided by 8 minus 3 factorial, just like the permutation. But we have one additional thing where I take that R value and I multiply the factorial of it as well to the bottom of the fraction. So here I get 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 divided by 8 minus 3 is 5 factorial, so 5 times 4 times 3 times 2 times 1 times this extra 3 factorial, so 3 times 2 times 1. Again, the 5, 4, 3, 2, 1 cancels out. 3 times 2 is the same as 6, so that cancels out. So I just get 8 times 7. I get 56 ways. So notice here that I have 8 people in both these situations, and I'm picking 3 from them, right? I have n is 8 and r is 3 in both of these problems. The first one was a permutation problem. The second one was a combination problem. The numbers we got at the end were very different. We got 336 and 56. Combinations should always be a smaller number than the permutations because you're getting rid of all those things that are repeats of each other. In a permutation, ACD and CDA and DAC, even though they're the same letters I'm picking, are different situations because the order matters. Whereas in this combination, it doesn't matter. ACD is the same as DAC, is the same as CAD. So all of those things get removed. So from 336, we take out all of those repeats, and we just get 56 left that are completely unique.